Hello everyone, this is my video for Unit 1 Limits and Continuity for AP Calculus. Please like and subscribe my video. So let's talk about limits. The definition for limits is as x up getting arbitrarily close but not equal to c. The value of f of x approaches or equal to L. The notation for this limit is the Li and x approaches c of f of x equal to L. And there's also one-sided limit. There's left-handed limit and right-handed limit. The notation for them are limit of x approaches c from the negative side of f of x equal to L, and limit of x approaches c from the positive side of f of x equal to L. Well, that's a lot of information here. Let's dive deeper into what is mean for limits. Here's the graph of f of x equal to x squared. Let's find the limit of x approaches 0, the left-hand limit, and the right-hand limit. So looking at the graph, we see as x approaches 0 from both sides, f of x is getting right here, the point of 0, 0. So we can conclude that the limit of this point equals 0. Well, what is one-side limit? Well, by the name, you can guess that we are only considering one side. The negative side symbols that we are only considering the values from the left side and totally ignoring what happening the right side of the graph. Let's see what happened here. The x value is starting large, and when x value approaching 0, we see f of x value getting smaller and smaller until it reaches at 0 at this point. So the left-handed limit of this limit is 0. And same thing as right-handed limit. We are totally ignoring the side, what's happening at the left side, only concentrating on the right side. We see f of x is already getting really large, but as x approaching 0, and we see f of x is getting closer to 0. So the limit of x approaches 0 from the positive side is also equal to 0. Alright, let's look at another example. Here, we see f of x is equal to sine of x when x is less than 0, and cosine of x when x is greater than or equal to 0. Let's find the limit of x approaches 0 from the left side of f of x. So we see here is a sine graph. F of x equals sine of x. We can directly substitute the value and see f of 0 equals 0. And we can trace the graph and see when x approaching 0, f of x is equal to 0. So we can say the left-hand limit of this graph is equal to 0. Well, what happened to the right-side limit? This is f of x equal to cosine of x. At f of 0, this graph is equal to 1. And let's trace the graph. Starting negative, it's getting more and more positive and approaching 1. So we can say the right-hand limit of this graph is 1. But what about this limit here? Well, this limit is a double-sided limit. Where it considers the value of both sides limit. So we see the left-sided limit is approaching 0. Left-sided limit is approaching 0. While the right-sided limit is approaching 1. So when the left-sided limit, x approaches 0 from the negative side of f x, is not equal to the right-side limit, the limit of x approaches 0 from the positive side of f of x, then we can say the limit of x approaches 0 of f of x does not exist. Finally, is that the two sides does not converge to one value, though the double-sided limit can be either 0 or 1. it's not a definite value, so it's not defined, and we can say DNE, which stands for does not exist. DNE. All right, let's look at table of values for limits. This is f of x equal to x squared. So one thing to note for tables is that as x getting closer and closer to a target value, which is 0 here, then the increment of x must be getting smaller and smaller. And we see here that this side is plus 1, this side is plus 0.3, and it's getting, increment is getting smaller and smaller. That's plus 0.04, and we see here really small increments here. And same thing as this side, because the table symmetry, that they increment the same, so they have a different increment, and this is an appropriate table to find a limit with. The table that you should not use to solve for a limit is when the increment is constant, or the concentration point of this table does not include your target value to find. Well, this table is appropriate, so let's find the limit of this point. Let's find from the right side first. See, it's getting 4 to 1 to 0.25, and this value really small. This value here really small. That value is approximately equal to 0, and we can see the trend. It's getting, see the trend here. It's getting less and less and less. It's approaching 0. So what we can say here is that from the positive side, it's approaching 0. Same thing as from the negative side. It's going smaller and smaller and smaller. At this value here, it's approximately equal to 0. It's approximately equal to 0. So we can say the limit of x approaching 0 from the negative side is equal to 0. What about the double-sided limit? Since the right-hand limit and the left-hand limit are equal, then we can say this exists and the value is 0. Alright. Algebraic manipulation. When we're dealing with the limit of a function, maybe it's not continuous. For example, the graph here is a piecewise function and it's not continuous at x equal to 0. And we might have other graph, for example, f of x equal to 1 over x. So what we want to do, we want to direct substitute the value when we are finding the limit. And we need to identify if it's a vertical asymptote, removable discontinuity, or it's defined there. So when the direct substitute, direct substitute, when it's undefined, it might give two results. One is 0 over 0. Another one is b over 0, where b is not equal to 0. Okay, so this maybe means is that we can still take the limit. This is actually called an indeterminate form. And this, we can tell that's a vertical asymptote. Vertical asymptote. Okay. So when we dealing with indeterminate form, we should use algebraic manipulation to solve for the limit. And there are 3 ways: factoring, solving by conjugate, and trigonometric identities. Let's talk about factoring first. When we are using this, when we are dealing with a rational function, where we can factor out some value. And The first thing we should simplify and by factoring. For example, this function, the limit of x approaches 0 of x squared minus 4 over x plus 2. We can factor out the top side. It's x plus 2 divided by x minus 2 over x plus 2. Don't forget the limit sign. Limit of x approaches 0. And we see this cancel out. So basically what we're finding is the limit of x approaches 0 of x minus 2. That gives you 0 minus 2, that's equal to negative 2. It is okay to simplify these values for limits because we're approaching some value but not equal to. Okay. And to the graph, to this thing here, basically we're fixing the hole. We're having a hole in the graph, and by simplifying this, we're basically filled the hole. And there's no more discontinuity at that point. It's about conjugate. Another method to solve is multiplying by its conjugate. So this happened when we were dealing with square root. Question with square root. And let's talk about an example here. What is the conjugate for 3 minus square root of 5x minus 1? Its conjugate is 3 plus square root of 5x minus 1. So what we can do here is multiplying both sides by the conjugate. Minus 1 over 3 plus square root of 5x minus 1. The purpose of this is try to simplify value and potentially cancel out this term here. Term at the other side of the square root function. That we can equal to, well, 9. Actually, let's try the limit notation first because we're solving for the limit. 9 minus 5x minus 1 over x minus 2 times 3 plus 5x minus 1. Remember, don't expand this. Don't expand this because we're potentially canceling out this term here. We're leaving is negative 5x plus 10 over x minus 2 times 3 plus square root of 5x minus 1. What is this equal to? Well, we can factor out a negative 5 from the numerator. Negative 5 times x minus 2 over x minus 2, 3 plus square root of 5x minus 1. Oh, what did we forgot here? We forgot the limit symbol again. It's approaching 2. Let's move aside. The limit of x approaches 2. What is this equal to? Well, we can cancel all this, so that's equal to the limit x approaches 2, negative 5 over 3 plus square root of 5x minus 1. We can substitute the value here. Negative 5 over 3 plus square root of 5 times 2 minus 1. We see that's negative 5 over 3 plus square root of 9. That's negative 5 over 6. Okay. About trigonometric identities. We're dealing with rational functions that include trigonometry, and we direct substitute give 0 over 0. We should consider what if we use the trigonometric identity to simplify the expression. So I will be covering about the most basic trig identities, and you can derive more based on them. The Pythagorean identity, sine square of x plus cosine square of x equal to 1. We have a square right here, basically means sine of x squared. nothing special. All right. And double angle identity for sine of 2x, that's equal to 2 times sine of x times cosine of x. And cosine of 2x, that's equal to 2 cosine squared of x minus 1. And it's also minus 1. It's also equal to cosine squared of x minus sine squared of x. Okay. Now we know this. Let's solve a problem. Let's say we have the limit of x approaches pi over 4 of cosine of 2x over cosine of x minus sine of x. We see there's a cosine 2x right here. So immediately, we should think about these two. If these two don't work, we should derive more based on these. And see which one should we use. We see cosine x minus sine of x. We see here, this one is really good because it's difference of squares and we can factor them out. So let's use that. Limit of x approaches pi over 4. That's equal to cosine square of x minus sine square of x over cosine of x minus sine of x. Is that equal to? It's different squares, so we can do pi over 4 cosine of x plus sine of x. And we multiply by cosine of x minus sine of x divided by cosine of x minus sine of x. We see here, we can cancel out this term here and the bottom term here. Cancel out, we leave with the limit of x approaches pi over 4 of cosine of x plus sine of x. That's equal to, well, square root 2 over 2 plus square root 2 over 2. That's equal to square root 2. Well, they don't have limits. If a, b, e, c, and k are real numbers, and limit of x approaches c of fx equal to d, and limit of x approaches c of g of x equal to d. So let's talk about the constant rule. This happens if we're taking a limit of x approaches some number c of a constant k that gives us k, right? Because when we have a graph of f of x equal to some constant k, it might look like this, a straight horizontal line. And because this graph is continuous, at any point, f of x is always equal to k. Okay, the constant multiple rule. So let's say we have a limit of x approaches some number c of k times f of x. Remember k is a constant? That really just equal to k times the limit of x approaches c of f of x. The k here is just a scalar. It's making the number larger by a scale of k. So we can totally ignore this, and we only need to concentrate on taking the limit of this side. And we just multiply by k. The sum rule. We have the limit of x approaches some number c of f of x plus g of x, That's equal to the limit of x approaches c of f of x plus the limit of x approaches c of g of x. Basically, you can take the functions out and calculate the limit individually and sum the values. Okay, the difference rule. It's basically the same as the sum rule, besides the plus sign here, we use the name sign here. The same thing, the limit of x approaches c of x minus the limit x approaches c of g of x. It's basically the same. The product rule. The limit of x approaches c of f of x g of x, that's equal to the limit of x approaches c of f of x times the limit of x approaches c of g of x. The quotient rule. The limit of x approaches c of f of x over g of x, that is equal to the limit of x approaches c of f of x divided by the limit of x approaches c of g of x. Basically, all these rules here, we can take the function independently, then we can calculate the value. Remember the value we didn't use, b and d? Well, we can use it right now. That's k times b, that's equal to b plus d, that's equal to b minus d, that's equal to b times d. Sorry, it's a capitalized d. And it should be b divided by d. Very straightforward. The composition rule. So let's say you're finding the limit x approaches c of f of g of x. This function is getting a bit more interesting because we have to take f of the limit x approaches c of g of x. Well, that's equal to e. But this f of, remember, limit of x approaches c of g of x equal to d. So f of d must exist for this theorem to work. And note that if the left-handed limit is not equal to the right-handed limit, try to use the theorem with left-handed limit and right-handed limit. If the results are the same, then the limit exists. So basically, let's say you're using the product rule here, and the left-handed limit at x equal to, let's say, 0, f of x equal to 3, and g of x equal to 5. But the right-handed limit, f of x equal to 5, and g of x equal to equal to 3. Well, when we multiplying, remember these are the limits here. When we are multiplying this value, they all give us 15. See, 3 times 5 equal to 15, and 3 times 5 equal to 15. Limit of x approaches 0. They all give 15. Even though the value for the left-handed and right-handed are not the same, but when the results of the left-handed and right-handed are the same, then the limit exists. Okay, this is one of the most interesting theorem, the squeeze theorem. So over the interval AB, possibly except x equal to c, such that a is less than c less than b, and f of x is less than h of x less than g of x, at the point c, limit of x approaches c of f x equal to the limit of x of approaches c of g of x equal to L. Then limit of x approaches c of h of x equal to L. Well, what does it mean? Here we have a graph. This graph here, that's x squared. This graph here is negative x squared. And this graph here is x squared sine of 1 over x. We see that x squared sine of 1 over x is always in between of x squared and negative x squared. And x squared is always above or equal to negative x squared. And based on squeeze theorem, if x squared and negative x squared are equal at this point, which we can see is at x equal to 0, then this function here must be equal to 0 at x equal to 0, while the limit of x equal to 0. Well, our example problem here is limit of x equal to 0 of x squared sine of x, sine 1 over x. And we see the previous 3 algebraic manipulation, they don't work for this example. And we can use the squeeze theorem. What do we know for the range of sine of x? Sine of x. That's between -1 and 1. So we know that -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. We multiply x squared by both sides. Negative x squared is less than x squared sine of 1 over x, which is less than x squared, at x equal to 0. That's equal to 0 less than x squared sine of 1 over x less than 0. So this limit here must be equal to 0 because it's 0 less than some number, the limit, and it's less than or equal to 0. This value has to be equal to 0. Alright, let's talk about continuity. What makes a point continuous? Well, it's the limit of x approaches c of f of x equal to f of c. And over an interval for every point in the interval is continuous. So basically, if the interval over a to b is continuous, every point inside of a to b, closed interval, is continuous. Now let's talk about discontinuity. There's 3 types of discontinuity. There's removable, there is jump, and there's infinite. Well, removable discontinuity is basically whole. We see here, that's f of x equal to sine of x over x. It's a special limit we'll talk about later. We see there's a hole at this point. And the limit of x approaches 0 of this point, that's equal to 0. But it's undefined at x equal to 0. That's removable discontinuity. The jump discontinuity is our previous example we talked about. So of x equal to sine of x if x is less than 0, and cosine of x if x is greater than or equal to 0. At this point, the limit of x approaches 0 of f of x does not exist, because there's a jump from 0 to 1 at this point. Well, infinite discontinuity or asymptotic discontinuity. Basically, there's a vertical asymptote at this point. We see here there's a vertical asymptote. This is f of x equal to 1 over x. Has a vertical asymptote and x equal to 0. So it's a vertical asymptote. Well, infinite limit and behavior and horizontal limit, horizontal asymptote. They all talk about what happens if x is approaching infinity or x approaches negative infinity. They're all the same thing. If the degree of the numerator is greater than the denominator, well, we're talking about rational function here. Rational function here. And the difference of degree is odd, then we can say the limit of x approaches negative infinity, a positive negative of f(x), equal to negative or positive infinity. And the limit of x approaches infinity of positive or negative f of x equal to positive or negative f of x. Basically, we only care about the highest degree of the numerator and denominator of the rational function. If the degree of numerator is greater than the denominator and the difference odd, let's say the difference might be 3, might be 1. And if there's a negative, when we do the long division, the result, the leading coefficient is negative, then it's a positive infinity it will approach. How about even degree? If the limit x approaches negative infinity of f of x positive negative, that will equal to the limit of x approaches infinity of positive negative f of x, which equal to positive negative infinity. Why is that? Remember a quadratic equation that the end behavior is approaching the same sign. So when the difference of degrees even, the negative infinity and the positive infinity value will have the same sign. If the degree of numerator and denominator are equal, and the leading coefficient of numerator is a and the leading coefficient denominator is b, then the limit of x approaches positive or negative infinity of p of x divided by r of x is equal to a divided by b. So let's talk about example here. So let's say we have the limit of x approaches positive negative infinity of 3x squared plus 5x minus 2 over x squared. Well, based on this here, this must be equal to 3. But why? Well, we only care about this terms here. Let's see. Because the numerator is 3 times greater than the denominator, the limit will approach 3. In fact, when we divide the numerator and denominator both by x squared, that will be equal to 3 plus 5 over x minus 2 over x squared over 1. And taking the limit of x approaches positive negative infinity, we see this approaching 0. This one is also approaching 0. So they cancel out. Well, they're all 0. They add up to 0. So that leaves with 3 over 1 equals 3. Okay, the last theorem is intermediate value theorem. So definition, if a function f is continuous over a closed interval a to b, for any number L that's between f of a and f of b, there must be at least one point C in AB such that f of C equal to L. So what does it mean? Well, let's say we have a graph here. This is a continuous function here. Let's say that's x equal to a and that's x equal to b. That's f of a and that's f of b. For some number L, let's say this is L. That is between f of a and f of b. Well, in this case, f of a is less than or equal to L, which is less than or equal to f of b. There must be one point in between a and b, point C. This point must exist. Well, it's common sense, but we need to use intermediate value theorem for this unit. Let's look at example. Let f be a continuous function over the closed interval 1 to 4. What are the intervals that must contain at least one solution f of x equal to 0? Well, let's see. From 1 to 2, It's from -5 to 8. Well, it does contain 0. So we will say there is 1, 2. This interval must contain a value that f of x equal to 0. Let's see if we have more. 2 to 3, 8 to -4. Because we switch sign here, and it must cross f of x equal to 0. So 2, 3 is another interval. Let's see 3 and 4. -4 to -10. It doesn't cross sign here, so it doesn't reach 0. We don't guarantee it reaches 0. So we'll say these two intervals are the solution based on intermediate value theorem. However, if the question doesn't give you the function is continuous, then we cannot say that this interval must contain at least one value c, because we don't know what happened between. It doesn't say it's continuous. Alright, let's move on. Limits you need to memorize. Well, one limit we already talked about is x approaches 0 of sine of x over x. We already talked about it, it's equal to 0. So basically, the limit of x approaches 0 of sine of u times x over u times x, that must be equal to 1. That's one variation of this limit here. You need to memorize. And there's one more. The limit of x approaches 0 of cosine of x minus 1 over x equal to 0. And same thing, if we have a scalar near x, say cosine of u times x minus 1, there should be a multiply symbol, over u times x by a better u. Fix this, should be a point. That's also equal to 0. This limit you can derive using the squeeze theorem, but you should memorize them because it's kind of complex if you want to derive these limits during the exam. That concludes my review for AP Calculus AB and BC of limit and continuity. This is Unit 1, and I'll see you in the next video.